Hello, my name is Daan Huybrechts. I am the Program Director of the Master of Science in Mathematical Engineering. In this presentation, I want to tell you a few things about the Master and the structure of the program. First things first, the Master of Science in Mathematical Engineering is a 2-year master program in the Faculty of Engineering Science in Leuven. It is jointly organized by 2 departments. These are the Department of Computer Science and the Department of Electrical Engineering. This will reflect later on, as we will see, in the contents of the program. Why mathematical engineering? We believe that mathematics and mathematical models and techniques have become increasingly important in many parts and aspects of society, in particular in industry. Companies can simulate products before they're even made in order to make them better or more precise. They can apply optimization techniques to reduce costs. They can predict situations, control situations, apply security to e-products, internet products. Recently, a lot of companies have been gathering a lot of data of the products that they make. They may want to analyze these data, and again, they will need mathematical models and techniques to do so. We also believe that the world is multidisciplinary, and so is our program. The 2 departments that combine in the educational program have complementary expertise. That is one aspect. We also believe that the mathematics underlies several disciplines, and not just in engineering. And so in our program, you will see many courses from other programs as well. The idea being that a mathematical engineer can collaborate with other engineers. We believe that mathematics is a common language to do and to make things. It's a primary language for science, engineering, and industry. As Roel van Beumen, an alumni now at Berkeley National Lab, puts it, if mathematical engineering were a master in mathematics, I would never have chosen it. It is not a master in mathematics. It is mathematics for engineering. We always want to do things, understand things, and make things. It's just that we use mathematics to do so. What are some of the things that we consider making, or thinking about, or understanding? In our program, we focus on 4 tracks or disciplines. These are industrial process control, data mining, simulation and scientific computing, and cryptography and security. We have a project course in which many of these aspects are integrated into one larger project. After studying mathematical engineering, we see that our students go to many different places. They essentially work in all industrial sectors. It used to be the case that a lot of people in applied mathematics would end up working for banks and insurance companies, but they are no longer the biggest employer. Our students work in the automotive industry, in chemistry, fabrication, health. We see a strong demand for industry, for people with analytical skills, like engineers, with multidisciplinary views, and this is what we aim for. We aim for a mathematical engineer who understands mathematical foundations that are relevant in different applications, and who can collaborate with other engineers in the other disciplines. They can develop a common language, they understand each other. As an example, these are some of the companies that our students went to work for. They are also companies that are part of our Industrial Advisory Council. Every once in a while, they look at our program and come together and comment on the courses that we have, on the ingredients that they would like to see for better employment opportunities later on. You'll see some of these companies are big international companies. Some of them are smaller in a Belgian or Dutch context. I would like to say a few things about the structure of the program, but first, what is it that we expect from students coming to Leuven wanting to study mathematical engineering? Of course, and I think this goes without saying, that we expect a strong background in mathematics, mathematical analysis, in particular analysis, algebra, and analytical methods for differential equations. There are also 3 domains in which we assume some expertise. that you have learned in a bachelor program elsewhere. We rely on programming skills, on the one hand, because we have a scientific software course, on the other hand, because many courses require projects being programmed in some language, for example, MATLAB. We require some familiarity with signal processing, an engineering point of view of signals. This includes sampling, Fourier transforms, and filters. This also relates to the other aspect of system theory. We assume knowledge of Laplace transforms, input-output systems, perhaps basics of control theory. This is relevant for some courses that are compulsory in the program, like system identification, nonlinear systems, and advanced process control. We do realize that the combination of these three domains is not very standard, perhaps not very obvious, but we'd like to be clear about the knowledge that we expect. If you have any questions about this, feel always free to send me an email and ask, for example, listing the courses that you've already had. Onto the program then. You can find the full program online on the website of KU Leuven. The principles of our program is that we have a block of core education courses, around 40 to 50 credits. And then we have elective courses that we separate into technical elective courses. These are courses that will go very deep into a topic, as well as broadening elective courses. And here you widen your view, less deep, but broader. We have some general interest courses, like most master programs at KU Leuven, and a fairly large part of your master program will be the thesis. Now, one of the principles in this program is flexibility and choice. The elective courses cover 4 different tracks. Those are the tracks that I mentioned before and that I will say a bit more about in the coming slides. We like to think of a program as being broad, and we like especially to connect to other subdisciplines. That is where the choice comes from. And you will also see in our program optional courses coming from other engineering disciplines. We like our students to be able to use the mathematics that they've learned in the core education and apply them in a specific subdiscipline that may interest them. For example, some students pursue a master thesis in biomedical imaging. Other students pursue a master thesis in the analysis of sensory data from windmills, all the while using the same or similar mathematical techniques. So what are these tracks? The first track is industrial process control. You can think of the control of chemical plants, but also self-driving cars or automatic pilots in aviation. This relates to system theory and control. Data mining is a growing and popular track in the master program. There's a lot of data and a lot of knowledge to be gained by analyzing data, understanding data. Again, this can go in several different directions. You can think of medical data, bioinformatics, or sensory data. And very typically, you will apply some optimization methods or some techniques that you will recognize in the courses of our program, like support vector machines, neural networks, relevant linear algebra routines, or parallel computations. The third track involves scientific computing and simulation. A compulsory course that aligns with this track is the numerical simulation of differential equations. Simulation is important, for example, in simulating a model prior to actually building the first prototype of a system. This has become increasingly important in many companies that create products. The simulation allows the first prototype to be much better than it would have been without the analysis. Finally, the fourth track is cryptography. 2 courses relevant in our program are advanced methods in cryptography and cryptography and network security. I would like to highlight here specifically that KU Leuven has a very strong worldwide leading expertise in cryptography. For example, the AES, the Advanced Encryption Standard that is widely used in many communication systems that have to be very strongly secure, was developed at KU Leuven by Vincent Rijmen and Joan Damen. Vincent Rijmen, who still teaches several courses you can learn from the master. As an example of the broadening aspect, on this slide I've included a number of courses from other engineering programs. I've listed the engineering program where it comes from. These are elective courses that you can choose as part of a regular Master in Mathematical Engineering. Finally, I would like to refer you to a number of additional references where you can obtain more information. The website of the Department of Computer Science, the website of the faculty, or you can just contact me via email, and you see my email address listed below. I hope to hear from you soon.